In this video, we're going to work example problems where we simplify polynomial expressions. So either you're adding or subtracting polynomials or multiplying polynomials, not dividing polynomials because that would be, then you have a rational expression. We'll talk about rational expressions and simplifying those later. Okay, so now it's important to note that all of the processes we're going to use here to simplify these polynomial expressions, this isn't unique to just like polynomials at all. Not at all. So, okay, remember, like a variable term like this. This is you look at this is just a number. And really this could be any number, not just any real number, it's any number in the entire complex plane. It's a placeholder for a number. You take in some number, take it to the seventh, multiply by 2, and you're left with a number. So this is just a number. This is a number. Okay, now obviously it's a little bit different than just saying this is the number 30, right? Because it's a variable expression. So we have to understand how to operate with variable expressions, etc., add them and whatnot. But I'm just saying that this is just, at the end of the day, this is just a number. Okay, and so with these polynomial expressions, the properties of numbers that we're going to be using to simplify these expressions are these properties, right? The commutative, associative, identity, the distributive property. Okay, now, as we've talked about, this says real numbers only because we had, in the textbook, we hadn't been introduced to complex numbers yet, but these apply to complex numbers as well. And so the point I'm trying to make is that everything we're about to do here applies to any kind of expression with any kind of number, radical, whatever. So it's important to realize that. We're just practicing with polynomials here because we're just getting a sense for working with these terms, with these whole number, positive whole number exponents. But this is not, anytime we distribute, anytime we add and we flip, the order of terms when adding, that applies to any number in the entire complex plane. So not just when I'm saying number, that's any variable expression. That could be a placeholder for any number in the entire complex plane. Okay, so now here the main property we're going to use. Okay, so here the main technique we're going to use to simplify this is combining like terms. And again, as we've talked about, combining like terms, we developed the proof of how you combine like terms. That comes straight from the distributive property, which again, all of this applies to any number in the entire complex plane. So you never have to look at, oh, well, what if these were radical expressions? Oh, well, we can't distribute. Oh, no, we can't do this or that. What if P could be a complex number? Oh, we can't distribute. Absolutely not. You can do any of multiply, distribute, divide. Exponents, that's just multiplication. Radicals, that's just the opposite of multiplication. Exponentials, logarithms, that's just multiplication and the opposite of multiplication. It's all addition, subtraction, multiplication, division. Okay? But the idea of how do you identify if you have two like terms? How do we know? So are these, what makes these like terms? Well, the coefficients don't matter because we know we can kind of factor out the coefficients. The idea is you look at the variable expressions, and the idea, they have to be exactly the same in every way, in the sense that, so these are exactly the same in every way, these two variable expressions. See, there's an x and a y and a z. The idea is we could pick any x, y, z trio in this entire 3D space, plug it in here, and ignoring the coefficients, and you're going to get the exact same number every time. That means they're like. And what you can see is that if they were different in any way, shape, or form, then that would mean that, okay, there's going to be cases where you can plug in an x, y, z trio, and they're not the same number. That means they're not like. And it's the same idea with radical, if you're trying to see if you have like radicals. Okay, so with that, let's just add these like we would if these were just regular numbers. Like 2 minus 4 plus et cetera, except we have to know how to work with variable expressions, and one of those properties is the like term, the idea of like terms. So, okay, well, we do, so we can remove this parentheses. Okay, and we could just now remove this parentheses. Okay, what are the like terms? So p to the 7th, there we go. So minus 8 plus 2 is minus 6. And you just leave it as p to the 7th. Okay, so we're done with that. Let's see, we've got these p to the 4ths. So minus 4 plus 6 is plus 2. Okay. Let's see, we've got a p squared on its own. Let's put it in descending order. Let's put it like a polynomial in descending order. Okay, now we've got plus 2p and we've got minus 5. Okay, let's subtract these two polynomials here. And yeah, this is a good example to where it's easy to get confused and think, well, okay, c cubed b and cb cubed, that's like terms, but no, because if we think about all the potential points, and that would be the CB plane, you can choose any CB pair, right, in this entire plane. Well, there's going to be points where if you plug them into this and plug them into this, you're going to get two different numbers. And so it needs to be the case that across the board, the variables are placeholders for the exact same number. Then they're like. And so the only way that happens is if they're the exact same in every way. But the coefficients don't matter, though, because you're kind of, we showed with the distributive property why the coefficients don't matter to have like terms. So, okay. So we've got, let's see, 0.05 c cubed b plus 0.02 c squared b squared minus 0.09 cb cubed. Now, okay, here it's like you can think about we're distributing a minus 1. And that's how you can kind of look at this. So plus 0.03 c cubed b, then minus 0.08 c squared b squared, then plus 0.1 cb cubed. Okay, so now let's bring the like terms together so we can, this is kind of confusing. We want to make sure we can see this clearly. So, all right, c cubed b, now we've got, let's see, 0.03 c cubed b. Okay, so those are done. Let's see. We've got this 0.02 c squared b squared minus 0.08 c squared b squared. Okay, minus 0.09 cb cubed plus 0.1 cb cubed. Okay. So now we can go ahead and add these. So these two, 0.05 plus 0.03 is 0.08 c cubed b. Then let's see, 0.02 minus 0.08 is minus 0.06. Okay, and then minus 0.09 plus 0.1 is positive 0.01 cb cubed. Now, okay, so but yeah, this is the final answer. But typically, we want to order polynomials in with the degree in decreasing order. But the degree of all of these terms is 4. 3 plus 1, 2 plus 2. So we'll just leave it like this. Okay, let's subtract this from this. So the idea is you're taking this and you're subtracting something from this, right? You're taking this polynomial and you're subtracting this polynomial from it. Okay. So we can distribute that minus. Okay, 1/4 minus 1/2. Okay, 5/8 plus 3/4 would be what? So 5/8 plus, let's see, 6/8, that's 11/8. Okay, 5 root 2 plus root 2 is 6 root 2. And there we go. Okay, now here let's multiply these two monomials, these single term polynomials. And so this is easy. We're using mainly the associative property. We can reorder the multiplication however we want, right? So it's like we could do minus 6 times 1/3 times a to the 5th times a squared times b squared. Okay, so minus 6 times 1/3 is minus 2. A to the 5th times a squared is a to the 7th. B to the 1st times b squared is b cubed. And that's it. Here, we're multiplying a monomial by a trinomial, but these are just numbers, right? You just distribute. These variable expressions are any of these variable terms are just numbers. So 7 times 2 is 14. M squared times n to the 4th is n to the 6th minus 21m cubed plus 28m squared. And there we go. Okay, here it's just distribution, right? But it's a little trickier because it's these terms that are both terms have more than one term. These are two. In this case, it's binomials. But again, I want to stress that this has nothing to do with this isn't just related to polynomials at all. You can do this with these are properties of numbers, any numbers. All variables we ever work with could be placeholders for real or complex numbers, and all numbers you can apply the distributive property. Okay, so 2x times x is 2x squared. 2x times 4 is 8x. Minus 5 times x is minus 5x. And minus 5 times 4 is 20. Okay, 2x squared now plus 3x minus 20. And there we go. Okay, let's see. 4u squared times 2u squared is 8u to the 4th. 4u squared times 3v squared is 12. Let's put the u first, like in alphabetical order. It's kind of how you think about doing it in general. Okay, minus, and then we've got 10u squared v squared, and then minus 15v to the 4th. Now, these are like terms. So we've got 12 minus 10 is 2. And there we go. Okay, 3y times 1/3 y squared is y cubed. Okay, 3y times 5y is 15y squared. Then minus 12y. Then plus 2y squared. Minus 30y. And then minus 24. Okay, so we've got y cubed minus 15y squared plus 2y squared. Okay, minus 12y minus 30y, and then minus 24. And there we go. Okay, here, what they want us to consider is the special case products that we developed for. It was between multiplying, we said multiplying binomials, so like a in general, that's a plus b. Okay, but it's important to remember that we developed these formulas using just the distributive property and the properties of multiplication. So these formulas apply to it has nothing to do with just polynomials at all, right? We developed the formula for a plus b times a minus b, where a could we were in general talking about when we developed these polynomials, but a could be, the idea is like a could have been any polynomial term, b could be any polynomial term. We developed the formula for a plus b squared and a minus b squared. But again, to do this, this is all distribution and addition, subtraction, multiplication. So you can, any number, any kind of expression obeys these formulas here. So, okay, but here we've got, so we can look at this as a minus b and a plus b. Okay, and now we see we have the conjugates. We're multiplying these two conjugates, where it's just, you have the a term on the left, the b term on the right. You just flip the sign in the middle, the addition subtraction sign. You're multiplying conjugates. So we know that what this is going to be is a squared minus b squared. So in this case, a is 4x and b is 5. So a squared we can see is 16x squared, and b squared we can see is 25. And there you go. Okay, here we can see we've got these two conjugates, a minus b, a plus b. So what's a squared? That's going to be 9w to the fourth. What's b squared? That's going to be 49z squared. Okay, once again, you can see we're multiplying two conjugates. So what's a squared? That's 1 over 25c squared. What's b squared? That's going to be 4 over 9 d to the sixth. Okay, here it's just we're doing a minus b squared, where you can see a is 5m and b is 3. B is 3 because it's a, the formula is a minus b, so b is just 3, right? A minus b. So okay, the result is going to be this perfect square trinomial in the case, since we're doing this with a polynomial. So that is a squared minus 2 times a times b. So 2 times 5 times 3 is, so a, 2 times a times b, and then plus b squared. And there we go. Okay, here we've got a and we've got b. We can see a is 4t squared and b is 3p cubed. We're going to get this perfect square trinomial, except we're adding now. So, okay, a squared is 16t to the fourth. Okay, now plus 2 times a times b. So 2 times 4 is 8. 8 times 3 is 24. 2 times a times b, so t squared p cubed, plus b squared, 9p to the sixth. And there we go. Okay, w plus 4 cubed. So we can do this. W plus 4 times w plus 4 squared. Right now, let's square this. We're going to get a perfect square trinomial. So w squared plus 2 times a times b. So 8w plus b squared. Right? This is a, this is b. Now we just distribute here. So w times w squared is w cubed plus 8w squared plus 16w plus 4w squared plus 32w plus, and let's see, 16 times 4, 64. Okay, so let's see, w cubed, now 8 plus 4 is 12, 16 plus 32 is 48. Okay. Okay, we can look at this like, so if a is equal to u plus v and b is equal to w, then what do we have? We have a minus b times a plus b, which we know is a squared minus b squared, this difference of squares. Okay, so what we know, b squared is w squared. That's easy. So what's a squared? What's going to be that perfect square trinomial? So u squared plus 2 times u times v plus v squared. So, okay, a squared minus b squared. And there we go.